When a basis B is chosen for an n-dimensional vector space V, the associated coordinate mapping onto Rn provides a coordinate system for V. Each vector x in V is identified uniquely by its B coordinate vector, and that notation is x in a bracket sub B, B coordinate vector. The B coordinate vector is a name for vector x that lists the weights used to build x as a linear combination of the basis vectors in B. Sometimes we have to change bases from B to C to aid in solving problems, and so that's what we're going to look at in this section, is how to change bases. Consider two bases, B and C. B has two vectors in it, B1 and B2. Base C has two vectors in it, C1 and C2. So we're going to consider these two bases for a vector space V such that B sub 1 is equal to 4 times C1 plus C2, and B2 is equal to negative 6C1 plus C2. Excuse me. All right, so these B vectors are there in terms of C. Suppose x is equal to 3b sub 1 plus b sub 2. That is, the B coordinate vector is 3, 1. You take the coefficients, that 3, this unwritten 1, and you make a column vector. Okay, so now with all that information, we're going to find x sub c, the C coordinate vector. Okay, so the C coordinate vector, we're going to write x as 3b sub 1 plus b sub 2, and a little subscript c for the C space. Pull out your scalar 3, and we're going to break these two up. 3b sub 1 C plus b sub 2 C. Okay, now that 3 and this unwritten 1, if you were to peel those off, you can put a column vector of 3, 1. That's your B coordinate vector that was given up here, 3, 1. And what that does is that leaves B sub 1 and B sub 2. For us, B sub 1 is 4C1 plus 1C2, so those coefficients are 4 and 1. And again, that's from B1, you have 4 and 1 as coefficients. B2 has coefficients negative 6 and 1 respectively, so you can make a column of those, negative 6 and 1. Multiplying by your B coordinate vector, we're going to take this matrix times x sub b, and then that gives us x sub c, or more correctly, the C coordinate vector 6, 4. Theorem: let B be the set of vectors B1 through Bn, and let C be the set of vectors C1 through Cn. And we're going to let these two be bases of a vector space V. Then there is a unique n by n square matrix. The notation's a little tricky. What this does is we're going to have a matrix. It's called a change of coordinates matrix, but it's going to let us change base B to base C, such that, and here's an equation to remember for later, the C coordinate vector is going to be equal to this change of coordinates matrix from B to C times your B coordinate vector. And I know the vocab's really deep in here, so just be patient with yourself, and with enough practice it'll come along, I promise. The columns of your change of coordinates matrix are the C coordinate vectors in the basis B. On our previous example, we had B sub 1 and B sub 2, but they were written in terms of C1 and C2. That's what that means. Okay, so your change of coordinates matrix is made up of your B columns your B vectors that are in terms of C. B vectors that are in terms of C. And that matrix is, again, I've already said it, it's called the change of coordinates matrix from B to C. Be very careful. That notation has a backwards arrow, a left pointing arrow, B to C. Visually, you take a vector in some vector space V, you take any vector, then when you want to go to Rn, you can use the C coordinate matrix to get you there. Same thing if you want to go from B, use a B coordinate vector to get X to be X sub B. Now to go from Rn to Rn directly, you multiply X sub B, you multiply it by your change of coordinates matrix. The columns of your change of coordinates matrix from B to C, those columns are linearly independent, and it's also, because it's a square matrix, it'll have an inverse, and that notation is change of coordinates matrix from B to C inverse. You just put you a little -1 up there. The C coordinate matrix is equal to, and we've already discussed that up here, your change of coordinates matrix times your B coordinate vector. And your B coordinate vector can be written as the change of coordinates matrix from B to C inverted times your C matrix vector. C coordinates vector. Okay, so let's do another example. Let's let B sub 1 equal -9, 1. B sub 2 equal -5, -1. C sub 1 is 1, -4. C sub 2 is 3, -5. And we're going to consider the bases for R2 given by B is equal to B1 and B2 vectors. C is equal to C1 and C2 vectors. We're going to find the change of coordinates matrix from B to C, and that's this notation. The matrix P, and we're going to change from B to C, involves the C coordinate vectors of B1 and B2. So we're going to let B sub 1 sub C equal x1, x2. B sub 2 C is equal to y1, y2. So by definition, if we take the two column matrices C1 and C2 and multiply it by x1, we get B sub 1. Notice that notation here, the C and C. And C1, C2 times y1, y2 is B2. So that is isolating that B2. Once you've got your B1 and B2, we're going to set up and solve an augmented coefficient matrix with B1 and B2. Okay, now it's important to note the order here. Up here it's P, note the arrows from B to C. This is important when you set up your columns. Your C and your B will stay in the same order as this. So if it's listed B pointing at C, right to left, just make sure your B's are on the right and your C's are on the left. Taking your two column vectors C1 and C2, you set those up here, then you augment, and then you put in the two vectors for B1 and B2, -9, 1, -5, -1. Row reduced echelon form, or trying to create a diagonal of ones, if you use your graphing calculator or an on the website calculator for matrices, either way you want to do it, once you row reduce the C columns and then the B columns, you actually get an identity matrix, which is great news for us. these two columns make up your change of coordinates matrix from B to C. And that format is identity augmented with that change of coordinates matrix. So anyway, you got to be careful when you set up the order. If it's B pointing at C, note the arrow. Your B's will need to be on the right, C's on the left. B's on the right, C's on the left. Set up your column vectors, row reduced echelon form, and it's the last two columns you're after. Now if you were to upgrade to R3, it would be the last three columns and a 3x3 identity matrix here. Okay, so let's check out another example. It's very similar. We've got B1, B2 column vectors, C1 and C2, and we're going to consider the basis for R2 given by those two bases, B and C. To find the change of coordinates matrix from C to B, this time we're going to put the B column vectors first, augment that, and then put the C column vectors last. Once we row reduce echelon form, then we're going to have the identity matrix in the first two columns, and then we'll have our change of coordinates matrix in the last two columns. Setting this up, again, be very careful. Make sure that arrow is pointing right to left, so your B's go first, C's go second, B's first, augment, C's second, row reduce echelon form, and we get the identity matrix in I2. These last two columns, 5, 6, 3, 4, that's your change of coordinates matrix from C to B. Now, if you happen to know one or the other, and this time we know the matrix from C to B, the coordinate matrix, you can actually invert these because the columns are linearly independent and they're square matrices. So if you wanted to go the other way and go from B to C, but you know C to B, you can just invert that. Another option would just be to reverse and put your C columns first, followed by your B columns. You can do it either way. If you know the matrix, invert it, and then your coordinates go the opposite way. If you just want to purely set it up to go from C to B, you can do it like we did above and set up an augmented matrix, row reduce echelon form. You'll get an identity matrix on the left half, the change of coordinates matrix on the right half. I'm just choosing to invert. So if I take this matrix from part 1, invert it, and then you'll probably get decimals if you use the TI-84. You can convert those to fraction by hitting math and enter twice. But anyway, once you've inverted the change of coordinates matrix from B to C, after it's inverted, then they go from C to B. Excuse me. Invert C to B, invert C to B, and then you get B to C. I'll get it out here in a minute. In a polynomial P sub 2, where a square or degree 2 is going to be your highest, we're going to find the change of coordinates matrix from the basis B, which has 3 polynomials or vectors, but anyway, the degree is 2, and that's going to match here. We're going to, find a change of coordinates matrix from the basis B to the standard matrix, standard basis C. Then we're going to find the B coordinate vector for this particular vector. Okay, so first we're going to find the change of coordinates matrix from B to C. And that's going to be all of our vectors in B in order. So our first term from B, we have 1, -2, and 1. 1, -2, and 1. Our second part is 4 minus 7t plus 5t squared, but you just want the coefficients, 4, negative 7, 5. And then finally the third, 3 minus 4t plus 6t, 3 minus 4, positive 6. The vector that we're trying to find a b-coordinate vector for is negative 5 plus 9 minus 5t squared. Let's take these, because this is in the C format, negative 5, 9, negative 5. Given the fact that your change of coordinates matrix from B to C times the B coordinate vector is equal to the C coordinate vector, and we looked at in that theorem on a slide or two ago, a couple slides ago. But anyway, given this fact, you can solve by row reducing the change of coordinates matrix, and you're going to need to augment this, but we built the change of coordinates matrix in part A, part 1, and then we just use the vector we're supposed to change up here, xc, that's going to go next to it. Anyway, long story short, we take our change of coordinates matrix and our C coordinate vector, and we're going to augment and multiply. Well, actually, we're just going to augment and row reduce. I was thinking of another topic. Okay, so here's the setup. From part 1, we have these 3 columns. These were the coefficients from the 3 vectors in basis B. So those are our first 3 columns. The last column is the C coordinate matrix, and that's the one we're trying to find a B coordinate vector for. Negative 5, 9, negative 5. Row reduced echelon form, we get I sub 3. It's an identity matrix with 3 1s down the main diagonal. And your last column, once you've row reduced, is your B coordinate matrix. Okay, so this vector was the one we were after. Find the B coordinate vector for this given vector, and we did it. You just have to be careful in the process of setting up. The row reduced echelon form we've done several times in the class. That part's not difficult. It's just knowing which parts to set up and augment. If you have any troubles, email me. It's the best way to contact. If you have any questions, just feel free to ask. And of course, I want to help and wish you the best luck.